Welcome to another fireside chat with the experts. Today, I'm really happy to be here with my colleague and good friend, Dr. Glenn Thomas. And the topic for today is a continuation of the presentation we started last week, which is an overview on the basics of X-ray inspection. So the idea here is to give you an overall or an overview of how X-ray technology works and the many applications where X-rays are utilized. So last week, Glenn went over several different X-ray applications, some of the basics and the physics of X-ray inspection, and we stopped last week at the bottom terminator component. So just to give you a quick overview, a bottom terminator component is every component where the leads or the contacts are under the component. So the bottom line is you can't really see those solder points because they're being hidden by the component itself. And got to a point in why they exist, right? Why BTCs exist. Well, as technology evolved and microchips got denser and denser and denser, engineers, component engineers, put the leads or the contacts on the periphery of the component. So we've all seen, the components they were rectangular and have leads or contacts on both sides. And as time evolved, the flat pack was developed. So you had contacts on the four sides of the component. They were started to be square. There were some difficulties assembling them, but what happened is it got to a point where as the silicon development technology evolved, the density of those components increased, and as a result, the periphery of the component wasn't enough to put all the contacts. So the component engineers at the time in the 80s developed this bulk grid array technology. So the pads ended up on the bottom of the component. And here's a side view of that arrangement. So you have the components right here, right? That's where your silicon and all the electronic smarts are. And the interface to the world with the printed circuit board is done through these balls or contacts that are underneath the component. The problem, as we talked about last week, is that you can't really see those pads anymore, right? They are, because now they're being hidden by the encapsulation of the component. So X-ray technology became essential in the manufacturing of electronic circuits, because only with X-ray you can see through the component and visualize these solder connections, like you can see here on the right. And with that, and why do you need to do that? Well, you need to make sure that those solder connections are there to begin with, that they are there properly, right? You have enough solder on each one of those contacts, and that those solder points are not touching each other, thus causing short circuits. Well, we have. I would like to share with you the best and also the worst BGA or ball grid array X-ray image ever, right? Why is this the best and the worst? It's the best from an X-ray perspective and from a understanding perspective, because this one X-ray image has every single problem you can find on a BGA assembly, right? It's incredible. So it's and it's also the worst because it has all the defects you can imagine in one BGA assembly. So let's walk around this image and go over what the problems are. The first one you can see here is coplanarity. Coplanarity is can be visualized once you have this tilted view of the BGA, right? So if you look straight down with an X-ray, you have this two-dimensional view. And as you tilt the board or you tilt the sensor, you have this perspective view of the BGA. And that's what we're looking at here. We're going to go over more details We call that 2.5D, which is a made-up term developed by X-ray companies. But we're going to go over what's 2D, 2.5D, and 3D. But for now, just think this is a tilted view of this BGA. And as you look at that row of balls on that corner, on that side of the BGA, you see that this ball is fairly round, right? And as you move towards the right side of the BGA, the ball gets elongated. You have this hourglass shape forming up here. So what this physically represents, right, is that the BGA is like this, right? So that's the PCB is here, and the BGA is off, like taken off from the board. So this coplanarity is a big problem because it means that you have you wind up with no contacts in one side of the BGA and short on the other side of the BGA. Once the BGA, so what causes that, right? Once the BGA goes a reflow profile, there is a wide range of CTE mismatches that occur during the process. CTE is the coefficient of thermal expansion. So the CTE mismatch causes the potato chip effect, right? So the BGA basically can go like this if it's heated past its capabilities. So either the BGA or the board potato chip causing this effect, or during the reflow, the BGA can walk, and if not enough or a disproportionate amount of solder has been placed on different pads, you might end up just by the capillarity of the solder as it wets, you might end up having this effect. Big problem. It's definitely something that has to be inspected and looked at. Short circuits are fairly straightforward to recognize. So here you have two balls that have been shorted together. Head and pillow is a difficult one to see and to find because head and pillow is that problem where the board, your assembly works sometime, and sometimes it doesn't work, right? Usually it works when it's in your shop while you're making things, right? You test it and it works, you ship, and your customer says it doesn't work.
Back, you test it, and guess what? It works, right? And because this is a problem where the ball sits on the pad, right? And it makes contact once in a while, right? It depends on, it can depend. We've seen a situation, for example, where the test jig that was testing the board was enough to push the BGA down and make contact. As soon as relieved from the jig and you ship to the customer, that contact opened, right? And now the board doesn't work. So you bring to our facility, you test on the jig, and works perfectly fine because that jig is applying physical force onto the BGA to make contact. You ship to the customer, you don't have the jig, it doesn't work. So it's a very hard problem to diagnose because this intermittent functioning. And it's called head and pillow because it resembles a head in a pillow, right? It just rests and opens from time to time. Again, another defect mode that requires a tilted view. And again, very hard to diagnose, very hard to find. But when you find it, it can signify insufficient reflow, right? Because you weren't able to wet the ball onto the pad. In a situation like this, since you have coplanarity, it might mean that we didn't have enough physical contact between the pad on the board and the ball itself to properly wet and make the metallurgic contact that you need to have a reliable solder joint. Moving on here, on the side of the BGA, you have open. An open is a good case scenario for a head and pillow defect. What do I mean by that? It means that in open, you really don't have a connection. No matter what, the ball is sitting high, the pad is here, and you don't have any connection. It's a best case scenario from a heading pillow because you don't have to worry about this on and off connection. It's always going to be off. Splatter is something that happens when usually signifies extreme, too much heat in your reflow, and the bubbles, they can be air or flux inside the balls. You just pop and splatter solder throughout the BGA. It's really, I mean, if you just look at this, piece of solder, you can say, what's the big deal? Just a little piece of solder inside my BGA is not a problem. Yeah, it's not a problem, except that as you...
It might lodge between the power and ground, for example, VCC and ground, causing a short and causing a mass, malfunction. So you can't, it's not a reliable assembly and should not be allowed. Moving on here, solder mask problems are not straightforward to recognize. A solder mask issue. So let's go back. What's a solder mask? So you start with a PCB, right? You have your board, and the board has copper traces and contacts, land pads where the BGA is going to sit on. Now, you have a solder pad and you have a trace that connects to the solder pad. Now, if you just put a little solder on the solder pad, the solder is going to run on the trace. And as we said earlier, you need that volume of solder so that you can keep the separation between the PCB and the BGA. So to avoid solder from running through the trace of each pad, we need to put a mask on top that's called a solder mask. So this mask that covers all the traces and just leaves the pads for each BGA ball, right? And what happens is that if the pads for some reason if the solder mask is defective, that solder is going to run through the copper trace, and as a result, you're not going to have enough solder volume to keep the separation between the BGA and the PCB. And as you have the discontinuity, this inconsistency of solder volume, you wind up with opens or even heading pillow. So that's a big problem. It can be a defect on the PCB manufacturer itself, but it can also be excess heat in your reflow profile, which cause the mask to lift, right? You have the peeling off the mask, and that allows solder to go like under a rug and potentially cause a lot of problems on that assembly. Voids are, it's a holy grail of BGA inspection. That's the very first thing you look for are voids. Too much voiding is a problem. Why? Because this. So what are voids? Voids are areas of the solder ball. They're occupied by either flux or air, right? So it's like, imagine a bubble of air, a bubble of flux inside the solid object. So that bubble, right, is if it's big enough, as the assembly goes through a temperature cycle, as things get hot and cold, right? Imagine your car in the morning, and then in the middle of the day, can go from 30 Fahrenheit to 90 Fahrenheit in one day, right? Which is a very aggressive temperature cycle. Well, that bubble has coefficient of temperature expansion, right? It moves, expands, and contracts at a certain rate. The solid object around it, which is a solder ball, has a different CTE. And this guy here, this bubble, is going to expand faster. So as things heat up and contract, you can imagine that now this solid object is going to be moving as well. And guess what? You don't want this thing moving, right? Because you're going to create cracks, and eventually you can separate the ball, shear the ball away from the BGA or from the PCB. So voids are, in some situations, hard to avoid, but they should be minimized. And there are different standards. IPC 610 has specifies a percentage of voiding on the BGA that you can have as a function of what the class of product you have, class 1, 2, and 3, which is a function of how reliable that assembly has to be. You can imagine that if you are manufacturing a toaster that's going to your kitchen, the requirements are very different from a real reliability standpoint than if you are making a toaster that's going to go on an airplane or a submarine, right? So different electronic assemblies have very different reliability requirements, and voiding is a part of that reliability composition. The shape of the ball, as you can see here, is a good indicator of wetting of the ball. So wetting, I don't know if you guys just go over it. Wetting is the ability of a solder to connect and run on a specific pad, on a specific metal. In this case, the solder onto the pad of the board. You want to see a shape that is round or oval. That's what we're looking for on a BGA inspection. An odd shape like you see here in the image represent that, and as a result, you ended up moving on top of the solder mask and creating this odd shape. And finally, you have missing balls. So missing balls, as you can imagine from the name, is when the ball is just not there. And when you're attaching the BGA onto the board, the BGA has the balls already onto each one of the pads, and you can either put flux on the board or you can stencil some fresh solder onto the board. And then when you mate the BGA onto the board, you reflow the solder wets and it connects. In the situations like this, often happen when the balls on the BGAs get knocked down accidentally because mechanical shock, because from picking up from the tray and putting on the board, in that process some of the balls got dislodged. We also have seen counterfeit BGAs where in the process of counterfeiting the BGA is removed, it's cleaned, and when new balls were attached or reflowed onto the BGA, the wetting wasn't done properly. So the ball doesn't really stick to the BGA and ends up falling fairly easily, causing a situation like this. So we have a whole session of this fireside chat about counterfeit detection, and we're going to cover that at that time. But for now, keep in mind that if you see missing balls, it shouldn't happen, right? It really shouldn't happen. If it's a brand new BGA, you shouldn't see any missing balls. If there are missing balls, it's very likely this BGA has been reworked at some point. By the way, feel free to leave your questions on the chat, or if you want to raise your hand, you can get unmuted and I'll be more than happy to address your questions. All right, so one of our pet peeves here at Creative Electron is that when people are designing boards, designing electronics, they really should think electronics design in a three-dimensional way. Why? Because if you think about electronic design, or when you're designing a board, if you think about how the board's going to be inspected with an X-ray, it can save you a lot of money. Let me explain why. Because as you add complexity to your an overlap between the top and the bottom layer, as you add more complexity to the board, the complexity of the equipment inspecting the board is also going to grow, right? So you can go from a simple 2D X-ray system that's going to cost you X to a 2.5D system that's going to cost you more than 2.5X, to requiring a 3D, so a computer tomography for a higher complexity. So if you can, let's go over some of the examples where we're going to show you how small changes on the design of the board can save you a lot of money in the inspection of the board once the board is built. So here's a good example. It's a 2D, two-dimensional, straight down X-ray of a ball grid array. And I want to point your attention to these balls here. You see this one here, that one there, this one, that one, this one. So you have several locations where decoupling capacitors, right? These components here are capacitors. By the way, how can you tell apart capacitors and resistors on an X-ray? Capacitors have a very dense dielectric, and as a result, they are very radio opaque, which shows very dark on an X-ray image. So these dark components here, these are capacitors. The light ones, on the other hand, resistors, are ceramic resistors, are very light and not radio opaque at all. So they show basically transparent on an X-ray image. And you can tell they're there by looking at the fillet they leave on the pad. So that's a resistor, capacitor, 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 and so on. So anyway, to minimize noise on the BGA, on the circuit on the BGA, you need to add a capacitor, right? Basically, a low pass filter on your power supply to make sure the power supply doesn't have enough too much ripple. And to minimize the inductance or the impedance between the pad on the BGA to the capacitor, what you do is you try to place the capacitor as close as possible to the balls, to the contacts, right? And what people end up doing, or designers end up doing, is perfectly aligning capacitors onto the balls, which makes very hard to inspect with a 2D X-ray, right? Because you look here, you can tell if this is a short
or a capacitor, right? So it makes life very, very hard for a 2D X-ray. Now, with a 2D X-ray, you can make a determination if these are legit shorts or just a capacitor sitting there. So what we have to do is to go ahead and tilt the board to get us a nice perspective, right? 2.5D. Now, this is a more expensive X-ray machine. You need more time. You need the right angle. You need, a more better trained operator to make that determination. As you can see here, let me go back and forth between those two images, and you can see here is that take a look at this. It looks like a big capacitor, right, hiding several balls there. So as we tilt, you can see there was one short that was being hidden by that big capacitor, right? And you can actually see that some of this, as we tilt, these are legit shorts. They're not capacitors, right? So it's very important that if you can, what we're suggesting here is that you shift or offset those capacitors, if possible, outside BGA, right, and bring traces in, or at least shift them away from the ball just enough that we can separate what's a BGA, with a ball, a solder ball, and what's a capacitor. So we looked at what a 2D inspection is, straight down view with the X-ray imager. We saw what a 2.5D, which is tilting the sensor, or tilting the table, or the stage, to give that perspective view, a tilted view of the image. So what's 3D inspection? What is computer tomography? So there's a wide range of ways that you can collect this tomographic or 3-dimensional perspective on an X-ray image. This is a fairly straightforward one that is very intuitive to understand. So let's go with this one for now. So imagine you have three objects, right? You have this blue object, the pink, and the red. So you have a square, a circle, and a triangle. And this can be the ball of the BGA, the PCB, and a capacitor on the other side of the PCB. So bottom and bottom layers of the same assembly. Now let's look at let's look at perspective one here. So this arrangement, the sensor and the source are going to make this movement, right? One is going to rotate clockwise, the source is rotating clockwise, the sensor is rotating counterclockwise. And in that arrangement, you have many tilted views of that stack, the same stack of objects. So in perspective one, the square is on the top, the circle is in the middle, and the triangle is on the bottom here, right? That's perspective on the X-ray sensor of those three objects. As we move the source and the sensor, you can see how the square, circle, and triangle separate differently. So they do this dance and they separate and come back together, right? And that's a function of the projection of the source and the sensor onto that stack of samples, right? That's pretty straightforward. Now, since you don't know where those things are, you don't know where your sample is, right? But you do know where your source is and your sensor, right? You know where your imaging train is at all times and exactly what angles and what projections you're imaging at. And as a result, you can, by doing some simple arithmetic on each one of those images, you can separate the top layer to the bottom layer of your board, right? And in this example, we have a QFP here on the top layer and a resistor on the bottom layer. And that fillet of the resistor is masking a potential short between those two pads of the QFP. So by applying this 3D tomography, you separate the top and the bottom to have a clear idea of the top side and the bottom side, thus clearing this arrangement from a potential defect. So to make it very straightforward, these are the three different X-ray modalities available for inspection. 2D, which is a straight down view of your sample. 2.5D, so that's when you tilt and you have the perspective view. And finally, three-dimensional, where you get a full volume of the sample that you can move around, decompose, and provide with a larger insight and complexity of the X-ray system grows as the number of dimensions grow. So with that, we're gonna open for any questions now. We're getting to the top of the half an hour here. Any questions? So we have a question here from John, which is, okay, yeah. So he's asking, what is half dimension? A half dimension doesn't exist, right? This is a made-up term that the X-ray industry came up with several years ago to differentiate between 2D and 3D, right? To call 2D is a straight down shot of the sample. 3D is a volumetric interpretation where you have X, Y, and Z information, right? Dimensional Z information, not only density Z information on your sample. So instead of pixels, you have voxels on a 3D representation. And half a D is a tilted view. So it's more of a marketing term than anything else. All right, we have another question coming up here. This one's from Dave. Does it matter where the voids are inside the bulb? That's a good question. Yes, it does matter. As you can see here, right, with a 2D imaging, you can see what the voids are, but you can't really tell. You have a solid ball. You can't really tell if that. If imagine that this that this is the solder ball and that the golf ball is the void. You can't really tell if the void is on the top as the interfaces with the board, or on the bottom as interfaces with the BGA. You don't really tell. With a 2D image, you're looking at a straight down shot. So by doing a 2.5D, you can tell that, for example, this void is right on the edge and right on the interface with the board. So that's a very bad place to have a void. And even if the void is below the threshold set by your quality group or IPC, whatever other standard you're going to use, even if it's below that threshold of 20, 25%, that's still a fail. It has to be rejected and reworked. Okay, so this is all the time we have for today. Thank you so much for participating and attending. Don't forget, next week we have another fireside chat with the experts. Check our website to see exactly what the topic is going to be, but it's going to be on Wednesday, 10 o'clock Pacific time. Glenn, thanks again for participating, and I'll see you guys next week. Thank you.
Joining us.
Clay, which one?